Hello class, happy Tuesday. Here we go. We're going to talk about ionization energy today a little bit more. I should have submitted page 6 and 7 as two separate assignments. They were due today to start a class. So we'll take a little bit of notes. I'll put the answer keys up on Canvas so you can check your work. And periodic table puzzle. So pages 8 and 9 in your packet. It's hard to do if we're not writing on paper. It would be hard to go back and forth and keep track of all this information electronically. So I have another activity we're going to do instead of page 8 and 9. It's another periodic table puzzle. So the assignment for today's class, once we're done with the notes, is to work on that puzzle and submit that before the start of class tomorrow. And then remember, tomorrow we got a 15-question multiple choice quiz. So 15-question quiz, 2 points each, worth 30 points in that other category. And here we go. So our question of the day, which would have the lowest first ionization energy? In other words, translation, which one would take the least amount of energy to remove the first electron, one electron from it? So lithium, beryllium, or boron. So we want to go over to the periodic table, figure out where these elements are located, because if we don't know where they're located on the periodic table, we can't answer the question. The periodic table, the location, is our basically guide to our answer. So look here, element 3, element 4, element 5. Which one would be easiest to steal one electron from? And so we could calculate the ENC and the effective nuclear charge. The pull on the outermost electron for neutral atoms is +1 for the alkali metals, is +2 for the alkaline earth metals, and the ENC for group 13 elements boron's family is +3. So look, they're all in the same period. They all have 2 energy levels of electrons. But lithium is only pulling on that outermost electron with a very weak +1 charge. So it'd be easiest to steal the electron from lithium. And so looking back at our question here, lithium is our answer. Lithium is the easiest due to the weakest charge, weakest effective nuclear charge pulling on the electron, making it the easiest to remove. And then look at our numbers here just to back that up. This is right from your notes. And I know it gets a little bit confusing here. Why is boron have a little bit less than beryllium? You know, there's a little bit more to it, a little bit complex reasonings. We're trying to keep it as simple as we can. So the general trend is that as you go left to right across the periodic table, electronegativities do change too, but ionization energies will increase. Alright, so lithium is the easiest to remove one from, and then noble gases are the hardest because the noble gases have the greatest effective nuclear charge, the greatest pull on their outermost electrons. Quick review of ion size. So remember, the big trend here is that if atoms gain extra electrons, they're going to get bigger. Their size will increase, and that's because now they have an extra negative charge, and those electrons, the closer they are to each other, the more they're going to repel. And so if you add an extra negative charged electron to the outside, now there's going to be more negative electrons, and they're going to want to spread out a little bit more. But the pull from the nucleus is still the same, right? The ENC is still the same. So the electrons are able to repel and push outwards, and that makes the atom bigger. And in red here, if atoms lose electrons, they will get smaller in size. And that's because there's fewer negative charges repelling each other, so they can be pulled closer together. But also, typically, you know, these are metals. Metals, if they lose electrons, they'll typically lose their outermost energy level. And if they lose a whole ring of electrons, like we mentioned before in previous videos and notes, they'll get much, much smaller. So for sodium has 3 energy levels of electrons. If it loses its outermost electron, now it only has 2 energy levels of electrons. And that'll make it tremendously smaller. So here we go. Here's an application question. And you're going to see a question like this on the quiz and a question like this on the test. So which is the smallest and which is the largest? So we have fluorine, which has a -1 charge. We got neon, which is a neutral. And then we got a sodium ion, which is +1. Like, oh my goodness, Mr. Lehman, how can we answer this type of question? I have no idea. And so look at our periodic table here. We're comparing sodium, we're comparing fluorine, and we're comparing neon. So how do we do that? Well, what I like to do is this. I like to compare the proton number and the electron number. So for instance, fluorine has 9 protons, neon has 10, and sodium has 11. How do I know that? Look at the atomic number, 9, 10, 11. From here, we got to figure out how many electrons it has. So if fluorine has a -1 charge, we actually call it fluoride ion. and it has an extra electron, so it actually has 10 electrons. Neon's neutral, so it has 10 protons and 10 electrons, which gives it a 0 charge. And then sodium has a +1, sodium ion, so that means it lost an electron, so it only has 10 electrons. So think this through, use some logic, make some sense of this. If every single one of these has 10 electrons, which one is going to do a better job, the best job at pulling in the electrons? With 9 protons, 10 protons, or 11 protons? Which nucleus would pull those electrons closer? Well, which one has the most force? The sodium, right? The sodium has the greatest number of positive charges in the nucleus, 11 protons. So 11 protons can do a better job of pulling in 10 electrons than 10 protons can, and definitely compared to 9 protons. So what does it mean? If you're the best at pulling electrons closer, that means that you're the smallest. And then 9 protons can do the weakest, the worst job at pulling those electrons in. And so what does that tell us? That tells us that the fluoride ion is going to be the largest of the 3. So the more protons and the same number of electrons, the more protons there are, the smaller the atom or the ion will be. And it's as simple as that. The sodium is the smallest and fluoride is the biggest. All right, that brings us to a little bit of notes here today. At the bottom of page 9 in your packet, bottom of page 9, we see this. Letter D, successive ionization energies. Some atoms will lose more than 1 electron to other atoms. So some atoms can lose 2 electrons, some atoms can lose 3 electrons, 4 possibly, but it's pretty rare. So successive ionization energy is the amount of energy required to remove electrons beyond the first electron. So we're saying, all right, we already stole the first electron. How much energy is it going to take to steal a second electron? That would be called the second ionization energy. How much energy would it take to remove a third electron? That is called the third ionization energy. All right, number 2, ionization energies will increase, usually dramatically, for every electron removed. That means that it will get harder to steal each additional electron. And so we're going to flip the page here. We're going to flip to page 10. And we're going to try to answer a question like this. All right, which element has an unusually high third ionization energy in period number 3? So what is this question asking us? What's this question asking us? Excuse me. Translation, which atom is much, much harder to steal a third electron from compared to a second electron? So the answer is magnesium. Now let's look at why this is true. So why is it so much harder to steal a third electron compared to a second electron? So what we want to do is we want to calculate the ENC on the third energy level electrons. What am I saying here, Mr. Lehman? What are you talking about? I'm saying right now, if I want to steal the first electron from magnesium, what is the ENC? What's the force that magnesium is exerting on that outermost electron? So what I would do, I would say, all right, we got 12 protons, it's magnesium. I'm going to minus, there's 2 in the first, 8 in the second, there's 10 core electrons. So 12 minus 10 is 2. So the ENC is +2. All right, so if I take that first electron, all I need to do is remove it from that +2 pole. Same thing for this next electron. So it'll be a little bit harder because there's not as many electrons on the outside. This electron then is going to be a little bit closer, but still, it's only a +2 ENC trying to remove those first 2 electrons. So first electron, pretty easy to remove. Second electron, a little bit harder to remove, but still rather on the easy side. But now those 2 electrons are gone, and so now magnesium has a +2 charge, so magnesium ion. So I'm just going to try to erase this the best that I can and not take too much time. There you go. Let's just do that. And I'll just close this back up. For those of you that would bother, it would bother me if I didn't close it back up. So now here's the deal. ENC on the third is +2. So what is the ENC, the effective nuclear charge, on the second energy level? So let's look at this. Now if we want to take a third electron from magnesium, we got to steal from the second energy level. Oh my goodness, that is like mission impossible. Why? Well, let's look at the ENC. There's 12 protons still in the nucleus, 12 positive charges trying to pull in electrons. Now there's only 2 inner electrons, right? The first energy level are now the inner electrons. Those are going to shield. There's only 2 of them, so only 2 of the 12 charge gets shielded. So 12 minus 2 is now 10 plus. That is crazy, right? 10 plus. That is a crazy high charge. This electron is closer, plus there's a 5 times greater charge. Instead of a 2 plus, now we have a 10 plus. So there's a 5 times greater pull on this electron, plus it's closer to the nucleus. That's a double whammy right there. And that is mission impossible. We can't steal a third electron from magnesium under any sort of ordinary conditions. So now if we look at our notes, page 10, let's confirm that. So let's look at magnesium. This is how much energy it takes to remove the first electron. Let's look at magnesium. Right, this 1, this is how much energy first electron stolen, second electron stolen, third electron stolen. Look at this. To steal the third electron, it's 5 times harder to steal it, approximately, than the second electron. The second electron is about twice as hard to steal as the first electron. So that means it's about 10 times harder to steal the third electron compared to the first electron, and that's just too much to overcome. And so magnesium, we'll see in nature, will lose 2 electrons, but never a third. Sodium, look at sodium. Sodium, it's really easy to steal the first electron. So it takes 496 kilojoules of energy to steal the first electron from sodium. If we want to steal the second electron, I sort of wrote over top of that, but if you're looking at your notes, you can see it. To steal a second electron from sodium, it would take about 9 times as much energy to steal electron number 2. Why is that? It's because sodium only has 1 valence electron. The second valence electron comes from the inner shell. Closer to the nucleus, and the ENC is 9 plus versus 1 plus. So the ENC is 9 times greater. And look, that's why it takes 9 times more energy. It's not a coincidence. All right, for the magnesium, looking at the numbers here. For magnesium, first electron takes 737 kilojoules of energy. Second electron stolen is also from the outside. It takes about 1,450 kilojoules of energy. And then that third electron comes from the inside, comes from the second energy level. It takes a tremendous amount of energy, 7,731 kilojoules of energy. I'm not going to write that out. I just gave you a verbal explanation for the last 2 minutes of why that's true. So finish that in your notes. And that is it for today as far as notes go.